There is one additional set of reactions of benzene rings, and that is under certain very extreme conditions, benzene rings can undergo nucleophilic substitution. This is not an SN2 mechanism, but in fact happens in one of two steps. Either it passes through a C triple bond C intermediate, known as a benzyne, followed by an addition of the nucleophile to either end of the CC pi bond. This is illustrated here by showing that our leaving group, chlorine, that led to our triple bond formation through an E2 reaction, was on the C13 labeled carbon atom. Our nucleophile ends up on either the C13 atom or next door to the C13 atom. The C13 is used to illustrate that we must have passed through an intermediate in which the carbon-13 center, where the leaving group was, and the adjacent center both are susceptible to attack. Common nucleophiles for this reaction include hydroxide, which could make a phenol, NH2, which could make an aniline, or RO-, which could make an aromatic ether. A second type of nucleophilic mechanism occurs when the nucleophile adds directly to the pi bond at which the leaving group is located, breaking aromaticity to make a resonance stabilized carbanion. This reaction will only occur if there are strongly electron withdrawing groups, ortho and/or para or both, to the leaving group site that will help stabilize the negative charge that develops. When the leaving group leaves from this intermediate, aromaticity can be reestablished to give us our product in which a nucleophile has replaced our chlorine. Note that neither of these nucleophilic substitutions involves a single step, or SN2. One involves an elimination to form an alkyne, benzyne, followed by nucleophilic addition to reestablish aromaticity. The second one involves a nucleophile adding to the site of the leaving group before the leaving group leaves, a non-aromatic intermediate anion, followed by the leaving group leaving and reestablishing aromaticity. We now have all the tools in our toolkit where we can make a whole variety of substituted benzenes. We still have to use our predicted reactivities and predicted selectivities in order to look at our preparation of any benzene rings with more than one group. And as a reminder, table 23.3 in your CARDI text, which indicates that when you have an atom with a lone pair of electrons on it, such as oxygen, nitrogen, or you have an alkyl group, that these groups all activate the benzene ring or make it react faster than benzene itself. They're activating with O- being the most strongly activating, and they direct ortho-para to themselves for the next substituent on the benzene ring. Halogens weakly deactivate the ring, that is, the ring reacts a little bit slower than benzene itself, but they still direct ortho-para due to donation of the lone pairs of electrons on chlorine-bromine iodide. On the other hand, any of our moderately or strongly deactivating groups, all of which have either a delta plus, or an entire plus on the atom adjacent to the benzene ring, these all make benzene react much more slowly. They are moderately or strongly deactivating, reacting more slowly, and they all deactivate the whole ring, but they direct meta. That is, the meta position is not as deactivated as everything else, so if you substitute on a ring with one of these groups attached, the next substituent will go predominantly in the meta position. This is illustrated in table 23.1, where our activating groups and our halogens, all the ones with the lone pairs of electrons next to the ring, along with the alkyl groups, all give predominantly products with a mixture of ortho and para substitution. The next group on the ring goes ortho or para compared to the original. On the other hand, if you have one of our moderately or strongly deactivating groups, the predominant position of substitution is meta. That is, your initial group is NO2, the second group is going to go predominantly meta.